Basically, it's going to present on from legacy to standard, LLM-assisted transformation of cybersecurity playbooks into CACAO format. Yeah, please start when you're ready.
Hello everyone, thank you for joining this talk. I'm Gurabi. I'm from RFIT and the University of Aachen, from Germany. I will present this paper about from legacy to standard LLM-assisted transformation of cybersecurity playbooks into CACAO formats. Without further ado, let's start with the motivation and the problem statement. As all of us know, the number of security crimes and security attacks are increasing every year, and this chart shows that until the expectation until 2028. For this reason, the number of incidents are increasing. We need to respond to them really fast, and it's really critical. But the investigation and decision making remains manual still. What happened in the Security Operations Centers or CERTs? They have some kind of documentation of best practices. When some incident happened, the admin tried to react based on those best practices, and they collect them in some documents called playbooks. But if we look closer to the playbooks, they are usually multimodal, they are diverse, and most of them are unstructured or semi-structured and human-maintained, make them, and also varying the complexity and abstraction level, make them really hard for exchange, for reuse in other organizations, and also for automation. As we again see the problem, we have static documents or knowledge bases lack details in them. That's why exchanging standardization and automation is hard, and that's why the solution would be machine-readable and standardized playbooks. But again, we face the other problem because most of those teams are overloaded. They don't want to work on new tasks, and manual playbook translation and transition to that machine-readable and standard playbooks are time-consuming, expensive, and error-prone, and most organizations are skipping that, ignoring that. We see the solution here to use large language models as the assistance for automation of the translation. Here in the picture you see when an incident, we have some type of incident, the playbook is created, we wanted to translate the playbook, then can partially automate them and also share the playbooks with other organizations. And this adoption in the second organization will be our future direction of the research. Let's take a look at some background about the standard playbooks. As I said, playbooks are usually in different documents. The operators should hop quickly the documents and also have some comments somewhere in YAML format in JSON or so. But CACAO somehow recently introduced in 2021. It started, but it's still not widely used. They try to structure the playbooks and try to make them machine-readable and also automatable. It has some strict formatting, like it's JSON-based, also forcing some kind of a standardization for UUIDs, for timestamps, and so on. And it supports some complex structures with different components, different type of steps like parallel steps and different kind of conditions like switch steps and so on, and referencing between different sections. And the key aspects of them are metadata for organizing and searching between playbooks, workflow steps, that's the core part of the playbooks, which has the process, the logic, and also the most important information and knowledge in the playbook. Agents and targets, which connect the playbook and the steps to the systems, to the people they are using, and the targets. And some variables, that predefined variables that can be used in the steps, connecting different things, something like path configurations, input secrets, and intermediate values. In our work, we focus on metadata, workflow steps, and variables for this translation. At the second part of the background, I list some prompt engineering techniques we wanted to talk about. The first one is a persona pattern. That's a simple prompt technique. You prompt the model to act as an expert in one field to bias the dummy language. The second one is template, that you enforce some strict schema with some placeholders in the output. Zero-shot chain of thought. Chain of thought is one reasoning method, but zero-knowledge chain of thought is like as simple as asking the model to think step by step and reasoning about the output. And reflection is coming with that. It's another reasoning technique that asking for reasoning and asking for justification of the output based on that reasoning. The direct knowledge injection is not completely a prompt engineering technique. It means that we also put the piece of information that we want inside of our prompt. And one-shot and few-shot prompting means we provide one or multiple input-output pairs to somehow teach the language model how to act what we expect as an output. Retrieval augmented generation, we have the previous slide. We need to talk about that much, but it's about fetching the external context. And manual decomposition is not a prompt engineering technique, but I put it here because it's important in our pipeline. That means breaking the task, complex task, into a smaller piece of software. In this work, we wanted to answer some research questions. First, we want to see if the vanilla models and the baseline LLM models can accurately translate the legacy playbooks different formats into CACAO format with simple prompt. Then we wanted to check if prompt engineering techniques can improve the results in second research question and third one. Second one, we focus on the syntax verification of that, the syntax accuracy, and the third one on the semantic accuracy of the results. And after that, we also have some feedback loop to feeding back the errors to the model and see if the model can improve the result by itself. Again, question number 4 is about the syntax accuracy result improvements, and in question number 5 we wanted to see if that correction also have a negative impact on the semantics. This is the conceptual approach here. We have some semi-structured or unstructured playbooks. Also we have the specification, we split the tasks, and giving the task and user input to our prompt engineering module, which has different prompt engineering techniques inside. Then we prompt the model, we get the fields and have a CACAO syntax checker, collect a list of errors, generate a full playbook. Then we send that to for UI for expert verification. In our work, in theory, the expert can also have detailed feedback on that, also put some inputs before confirming it and getting the exported playbook. But we only send send the feedback to the model for for getting the better results. In this work, we only send the list of errors as the automated way of improving the results to the module again and do this work iteratively. And for evaluation, we categorize the language models in 3 categories. First one, the small open source one, like Gamma, Mistral, and Llama. And we chose Llama 3.18 billion in that category to work on. In the second category is the small and mid-sized language models, but normally not open source, closed source ones, like Cloud HiCo, the Gemini Flash 1.5 Flash, and GPT-4 Mini, and we chose OpenAI one. And in the big category, we had Llama 4.05 billion and the latest Gemini and Cloud model and GPT-4 4.0. At that time, that was the last model of OpenAI. And we did the evaluation for syntax accuracy on the data set we developed, because we had the problem there was lack of data. We didn't have any pair of legacy playbooks in the accurate translation to CACAO playbooks. That's why we needed to come up with some playbooks. We had 40 structured playbooks as input and generated CACAO equivalent of that for this syntactic accuracy. We chose a subset of that, 10 playbooks, and manually crafted the CACAO reference as a ground truth for semantic fidelity test. And the metric for the syntax accuracy is just the number of errors in our syntax checker. And for the semantic fidelity is for text fields, we use Radu-Mihai. For the type fields, which has a specific text amounts, we use recall. And for workflow, we use normalized gravity distance, which is the graph version of the Radu-Mihai distance. And after that, we also do the syntax refinement for 5 iterations, and with the same data sets and with the same metrics. For the first research question, we had some early observations. We see if we remove task decomposition entirely, it increased the number of errors, the syntax errors, about 3 times. That's why we decided to keep it into our baseline. Also, if we directly prompt the model for a CACAO output by feeding the CACAO specification, we don't get any results conform to the syntax. That's why it makes it impossible and meaningless to count the number of errors. That's why we also keep the template-based prompting in the baseline method. Then it means our baseline is not just asking the chat UI to generate or translate our model, our playbook, but including that template and task decomposition. For the second question, for syntactic results, we got the best performance with knowledge injection individually, without adding the others. It has the best performance, at least for the OpenAI models. You see that it really reduced the number of errors. But in general, combining them has the average of 73% decrease of all errors in all 3 models. We had some problems with increasing the number of errors after reasoning, and we interpret that because after that reasoning, we got more semantically complex playbooks, and it means the playbook is not as simple, that has less errors, but yeah, got more errors, but also more semantically accurate. For smaller models, but for GPT-4o, also after reasoning, we didn't get any worse results. Yeah, in general, for the baseline, the small model, Llama model, performed good, but in general, after combining all the methods, all the techniques, it got better, but not improved in the level of OpenAI models. Then let's see the semantic results. For the graph distance, you see regardless of the combination or the cases, the best case is for GPT-4o. It's outperformed the others, and followed by GPT-4o mini, and Llama small model didn't perform very well. And also we had an improvement by around 10% for GPT-4o mini after reasoning case. And in general, combination of all techniques led to a slightly better results for all of the models. And for metadata, it's the combination of narrow language time distance and recall. For here in the first the graphical distance, the lower number is better for sure. And for the semantic accuracy, the higher number is better. And for metadata, you see the combination of the techniques really improve the results. And again, the best performance was for GPT-4o. After that, we had that syntax refinement, and you see in this figure that the solid ones, the black ones are before the refinement, and the white ones, white inside, is after the refinement. And for all the models, after 5 iterations, it got really better. And for OpenAI ones, it's almost 0 errors in syntax. For GPT-4o, it's exactly 0 errors, and for O-mini, for most of the cases, it's 0, but for example, for persona and reasoning is near to 0. And then we combine all the prompt engineering techniques, it got is converged to 0. But for Llama 3.1, it's also gets better, it's improved, but not close to 0. And we interpret that the size of the model, because that's really small, play an important role. And impact of that on the impact of syntax correction on the semantic accuracy, you can see here this chart is about normalized gravity distance. As you see, it's kind of constant. It didn't drop too much. We have a slight degradation in some cases, but not really considerable ones for all of them. But for the semantic accuracy for metadata and variables, we had some drops. For variables, only drops was for Llama model, and for the metadata, we had some drops also for GPT-4o and for O-mini, but again, the best performance stay for GPT-4 and bigger models. We had some lesson learned during this work. First was the design question about using retrieval augmented generation instead of injecting the knowledge. And because for that RAG, we only wanted to have the specification, CACAO specification there, and we find out it's not accurate enough, and it's better to directly put the knowledge because it's just one specification, and we know what exactly we want from the specification to put in the prompt, and that get better results. A specification conformance, we extract information in the structured schema and building playbook from that extracted information at the end. The playbooks are very long and complex with many dependencies. For the few shot prompting, the solution was just come up with the few shots for each of those subtasks. Otherwise, that doesn't make much sense to have the pair of input, the full input and output for the playbooks. Direct usage of validator output does not help to fix errors when input is missing. Which means in some playbooks you don't have some inputs that are mandatory or very relevant for CACAO playbooks, but we cannot fix that. The only way to fix it is to ask an expert to input that information. And it would be in the tool, but it's not in the evaluation. And about the confidentiality concern of the playbooks, we, for the future work, we wanted to fine-tune local and smaller models to open source models to see the difference and respect the confidentiality of the playbooks. Lesson learned about the results are sometimes are simple, like metadata extraction. Then the size of the model is not that important. GPT-4o Mini also can extract those as good, let's say, comparable to GPT-4o, but for more complex tasks like extracting workflow steps is more challenging, and GPT-4o really outperformed there. Okay, I can skip this one. We wanted to also integrate it with our playbook management tool and automate some steps. And for the conclusion, what we achieved is 84% decrease in the average number of syntax errors for GPT-4o. Also accurately capture the control flow with average of 0.15 graphic distance for GPT-4o. It's a good number, and iteratively reduce the number of errors, syntax error for OpenAI convergence to 0 after 5 iteration. The limitation was a small data set, evaluation only with 3 types of input playbooks, benchmarking only 3 models, translation of some specific components of CACAO, but not all of them, and lack of real baseline, which is not a limitation, but the results could be even better if we compare it with the just vanilla model with simple prompts. And for future work, we wanted to translate all the CACAO fields, evaluate more state-of-the-art models, comparison of these approaches with agentic-based and fine-tuning, identifying more process-related metrics instead of graphical distance, because graphical distance is really penalizing even if the workflow logic is the same, but the graph is different. And of course, generalizing the approach for other use cases and also other playbooks. Thank you for your attention.
I think we got time for a very quick question. If anybody got a question? No questions? Okay. Yes, because of the time, I got a couple of questions, but maybe I will discuss them offline because of the time. Okay. Once again, thank you.